In this demonstration I have a horseshoe magnet, a wire, and this wire is plugged into the voltmeter readings of my multimeter. So I'm actually reading volts here on the screen. As I take my wire and I pass it through the magnetic field, a potential difference is actually induced across the ends of the wire. This is called electromagnetic induction. I could increase the size of the potential difference by either using a stronger magnetic field, so using a stronger magnet, this is the only one I've got, or I could move the wire faster, or I could make a coil in the wire. So if I was to make a coil in the wire and pass that two ends of the coil through the magnetic field lines, then I actually get a greater induced potential difference. I'm now going to change the settings on my multimeter. I'm going to change it from being a voltmeter to measuring milliamps. So I'm going to change it to its milliamp setting. Now that the wire is in a complete circuit, when I pass the wire through the magnetic field, this time the induced potential difference is causing a small current. Now this small current in the wire being pushed by the potential difference is called the generator effect. I've now connected the voltmeter to a coil of wire within a magnetic field. This is the DC motor from yesterday, but I haven't actually got a power source to this one, so it is now going to act as a DC generator. As I spin the coil within the magnetic field, you can see a potential difference is induced. Now this is because instead of having I've still only got one length of wire, but instead of having a very short length of wire within the magnetic field, I've now got a much longer length or greater length of wire within the magnetic field. So every time the coil is turned, a much greater length of wire is cutting through the magnetic field lines. Now the magnetic field lines are actually going from the red side, the north side, to the south side. So imagine the lines going across in horizontal lines. As the coil is moved round, so it's roughly parallel with the magnetic field lines, there's very little voltage actually being induced. When I turn it to be perpendicular to the magnetic field lines and move it, a much greater potential difference is induced. This is because the wire is cutting many more field lines. In this demonstration I've got a simple generator connected via two wires to a simple motor, and as you can see, as I turn the generator, there's potential induced, which induces a current in the wire. So it's now the generator effect is inducing current in the wire, and the current is driving the motor. As I turn the generator, you can quite clearly see the motor turning. As I turn the generator in the opposite direction, the motor turns in the opposite direction. For this final demonstration, I'm going to use this small generator again. At the moment, it's not in a circuit, and it's actually very, very easy to turn. Now, if we touch these two wires together, it suddenly becomes really, really difficult to turn. This is because when I complete the circuit and I'm turning the generator, I'm actually generating a current within this wire. If there's a current within this wire, then there's also a current within this wire here as well. And if there's a current within this coil itself becomes an electromagnet. So I'm actually turning an electromagnet within a magnetic field. And it just happens to be that the magnetic field on the electromagnet is going to be in the opposite direction to the magnetic field here, and so they actually work against each other. This is actually a dynamo, which is a DC generator. This is because we have two brushes against the split ring commutator. In a alternating current generator, also known as an alternator, this setup here is slightly different, and the difference being is that it has two slip rings connected to brushes. Much better seen in the diagram. Now, in all the generators I've been showing you today, I've been spinning a coil of wire within a magnetic field. I could just as easily be spinning a magnet, or a magnetic field even, near a coil. Both will have the same effect as long as you've got one spinning near the other, then you're going to have an induced potential difference across the ends of the wire. Now, to summarise, the faster we're going to spin the coil or the magnet, the greater the potential difference. I could also increase the strength, or I could also increase the size of the potential difference by increasing the magnetic field strength or the numbers of turns on the coil within. Okay, thank you for listening, and it's probably time to go and do some work now. Bye bye.